Hello friends, in today's lecture I will discuss about luminescence spectroscopy. You all know spectroscopy. Spectroscopy is the interaction of light with matters, that is light matter interactions. Okay, then we should know what is luminescence. Luminescence, the term luminescence comes from the Latin word lumin, that means light. So basically luminescence is cold light emission, whereas incandescence is hot light emission. The luminescence is defined as an emission of ultraviolet, visible or infrared photon from an electronically excited species. Okay. Depending upon the mode of excitation, the phenomena luminescence can be categorized as follows. When the mode of excitation is absorption of light, that is absorption of photon, then this phenomena is called photoluminescence. When the mode of excitation is ionizing radiation, that is X-ray, then it is called radioluminescence. When the mode of excitation is chemical process, basically oxidation, then it is called the chemiluminescence. When the mode of excitation is cathode based, then it is called the cathodoluminescence. When the mode of excitation is friction and electrostatic forces, then it is called the triboluminescence. When heat is the mode of excitation, then the phenomena is called the thermoluminescence. Okay, thermoluminescence. When ultrasound is used as mode of excitation, then the luminescence phenomena is called the sonoluminescence. Okay, so we here see mode of excitation. The luminescence phenomena can be classified different categories. Okay, out of these different luminescence process, photoluminescence is an important process. Here we basically discuss the photoluminescence process. So after before discussing the photoluminescence, we also discuss the light matter interaction. As we read spectroscopy, that is light matter interaction. Light matter interaction are two types: scattering and absorption. Scattering are two types: elastic scattering and inelastic scattering. Elastic scattering is called the Rayleigh scattering, and inelastic scattering is called the Raman scattering. Absorption, the another light matter interaction is absorption. Absorption means absorption of light by molecule. When molecule absorbs light, then it goes to excited state. After going to excited state, the molecule relaxes back to ground state. When molecule relaxes back to ground state from electronically excited state, it emit photon. This process is called the photoluminescence, that is the emission. So emission is the results of absorption. Okay, so we call here we say photoluminescence is the results of absorption. Okay, the photoluminescence are two types basically: phosphorescence and fluorescence. Okay, phosphorescence and fluorescence. Basically phosphorescence is the excitation process where the molecule relax but de-excite from triplet excited singlet state to ground singlet state. When the molecule de-excite from first excited singlet state to ground singlet state, then this process is called the fluorescence. Okay, the process of photoluminescence, many photoluminescence processes, that is phosphorescence, fluorescence, are shown in Jablonski diagram. This diagram and these figures are extracted from Valor Molecular Fluorescence Spectroscopy book. You may also read or download this book from internet. Okay, here in the Jablonski diagram, we see different energy level. S0 is the ground singlet state, S1 is the first excited singlet state, S2 is the second excited singlet state, T1 is the first triplet excited state, T2 is the second excited triplet state. Okay, in every electronic state you see that many vibrational level. As we know, electronic state are consist with vibrational level. Okay, when the molecule absorb light, the molecule goes to different singlet excited state. Also the molecule goes to different vibrational level of the different excited singlet state. Okay, in first case here the molecule goes to different vibrational level of the S2 electronic state, And second case, the molecule goes to the different vibrational level of S1 electronic state. Okay, this process is called the absorption. Absorption takes place in 10 to the minus 15 seconds, that is femtosecond time scale. Okay, after excitation, the molecule relaxes back. When the molecule relaxes back higher vibrational level to lower vibrational level of a same electronic excited state, then this process is called the vibrational relaxation. Here you see vibrational relaxation process. The vibrational relaxation is also non-radiative process. Non-radiative process means no emission of photon. Okay, when the molecule goes to S2 level electronic energy level to S1 energy level, then this process is called the IC, that is internal conversion. That is internal conversion. Okay, internal conversion means transition between same spin multiplicity excited electronic state. Okay, that is IC. Okay, here it is IC as S2 to S1 electronic same spin multiplicity electronic system transition occurs non-radiatively. Obviously non-radiatively. Non-radiative transition means no emission of photons. Okay, that is IC. When the molecule reaches a particular vibrational level of first excited single state, that is S1 state, the molecule relaxes back to S1 state. This process is called the vibrational relaxation. This is also non-radiative transitions. Okay, when molecule reaches ground vibrational level of the S1 state, first excited single state, then molecule goes to or de-excite to ground singlet state. Okay, the transition from S1 to H0 state is called the fluorescence. When the molecule de-excite from S1 level to different vibrational level of H0 level, then the molecule emit photons, radiative transition occurs. This process is called the fluorescence, and fluorescence occurs in 10 to the power 9 second, that is nanosecond time scale. Okay, from S1 level another process can be happens. This process called the ISC, intersystem crossing. This is basically transition from S1 energy level to T1, or basically transition from S1 electronic state to T1 electronic state. Okay, okay, this process is called the ISC. Okay, ISC means intersystem crossing. Basically ISC is called a non-radiative transition from different spin multiplicity electronic state. Okay, S1 to T1 transition called ISC, or T1 to S1 non-radiative transition is called the ISC. Okay, but basically electronic transitions from different spin multiplicity system via non-radiative pathway is called ISC, intersystem crossing. Here S1 to T1 is shown ISC, the intersystem crossing process. Here it is non-radiative transitions because no lights emit for this transition. When the molecule reaches a particular vibrational level of T1 energy state, then the molecule relaxes back to ground vibrational level of T1 state. Ground vibrational level of T1 state. From ground vibrational level of T1 state, the molecule goes to different vibrational level of H0 state. Okay, this process is called the phosphorescence because the molecule de-excite from T1 state to H0 state and emits photons. And this transition is spin forbidden in nature because different spin multiplicity transition. So the time scale for the phosphorescence is relatively higher than fluorescence. Okay, phosphorescence time scale happens in microsecond to millisecond, that is 10 to the power minus 3 to 10 to the power minus 6 second time scale. Okay, the basic difference between phosphorescence and fluorescence is fluorescence basically occurs S1 to S0 transition occurs from S1 electronic state to H0 electronic state transition, and phosphorescence basically occurs T1 electronic state to H0 electronic state transition. Okay, the fluorescence lifetime are in 10 to the power minus 9 second, that is nanosecond time scale, and phosphorescence basically occurs in microsecond to millisecond time scale. Okay, okay, these are the ab absorption spectrum, and these are the fluorescence and phosphorescence spectra. And the absorption spectra are shown H0 to S1, H0 to S2 for here absorption band, and H0 to S1 for this. Here these are H0 to S1 transition are rate shifted relative to S0 to S2 transition, because for H0 to S2 transition energy gap is higher. As energy gap is higher, we know delta E equals to Hc by lambda. So this axis is lambda axis. So lambda is greater for H0 to S1 transition than H0 to S2 transition. Okay, this is the absorption band. Okay, and these are the fluorescence. As fluorescence occurs from S1 to H0 transition, so and phosphorescence occurs T1 to H0 state, and the relative energy of S1 and T1, from the relative energy of S1 and T1, S1 is higher energy than T1. So T1 to H0 transition is rate shifted than S1 to H0 transition. This is the fluorescence spectra, and this is the phosphorescence spectra. Basically, the excited molecule do different process. Basically, there are different possible de-excitation process of excited molecule. They after exciting, the molecule can emit radiatively from S1 to H0 level, that is fluorescence emission. Molecule can do intersystem crossing and shows phosphorescence. Molecule can transfer electron, molecule can transfer energy, molecule can form excimer, etc. This is the possible excited state phenomena that molecule does. Okay, basically these figures are extracted from Hello Molecular Fluorescence Principle and Applications book. Okay, now we'll know what is absorbance. Basically, when a monochromatic light is passed through a solution containing absorbing substance, then light is absorbed by substance. If the intensity of incident radiation is I0 and intensity of transmitted radiation is I, then ratio of I0, logarithm of ratio of I0 and I is called the absorbance. We also know Lambert-Beer's law. From Lambert-Beer's law, what is Lambert-Beer's law? When a monochromatic light is passed through a solution containing the absorbing substance, the decrease of intensity of light with pathness is proportional to concentration of solution and intensity of the light. The final equation of Lambert-Beer's law is A equals to epsilon L into C, where epsilon is the molar extinction coefficient, unit of mole, liter, mole inverse, centimeter inverse is the concentration, unit of mole per liter, and L is the path length, unit of semi. Basically it is 1 semi. L equals to 1 semi, basically path length. Okay, so A equals to epsilon LC. Okay, okay, so basically Lambert-Beer's law told absorbance equals to epsilon into CL. Okay, how we measure the absorbance value? For measuring absorbance value, we used spectrophotometer. From spectrophotometer, we got basically absorbance value by OD value, optical density. Okay, here it is the typical schematic diagram of spectrophotometer where we measure the absorbance value. There is a source of light. The light goes through the monochromator. Monochromator basically converts multicolor wavelength to single wavelength value, and from monochromator the light is goes to beam splitter basically do the split of light in two equal halves. Okay, two equal parts basically. Okay, first goes to the solution chamber, and second goes to the solvent part. Okay, basically basically this is the double beam spectrophotometer scheme. Double beam spectra, single beam spectrophotometer, there are two types of spectrophotometer basically, double beam and single beam. This is the typical diagram of double beam spectrophotometer. Well, one part of light goes to the solution and another half part goes to the solvent. From solution we know, from Lambert-Beer's law, uh, the absorbing species absorb some light and transmittance a fraction of light of incident radiation. Okay, if the path length is L, then A equals to log I by I0 equals to epsilon CL from Lambert-Beer's law. And basically here from this value the software does basically absorbance value of solution, and from the this actually absorbance value of reference is calculated. Actually software does this difference, two difference value, that is solvent solution minus reference value, that is absorbance of absorbing speed, that is equals to log IR